Hi, I'm Prof. Joe. This is part of my lecture on measurement technology. Again, dealing with standard technology today, talking about current sensors. Okay, first thing one thinks, having heard the other lectures or seeing the other videos I've made, is why talking about current measurement? We already can measure currents. We have some devices which can measure currents. That's true. And nonetheless, there are other sensors out there which are more easy to adapt to an existing electrical network, for one thing. And moreover, we have to somehow talk about the details, about the sensor details when measuring a current. So, thinking back, one way of measuring a current would be just using an ohmic resistor. What does that mean? Yeah, let's imagine the ohmic resistor is connected to an electrical network which drives a current I through it. Now what we can do, since we mainly only have devices for measuring voltages, we could measure that voltage over here, and now by that calculate the current by just using Ohm's law. You know R equals U over I, meaning that I equals U over R. By that we can measure currents. So we have a voltage measurement device, and using a resistor we can measure currents. Why is that important? The first important thing about that is out there are mostly voltage measurement instruments. Think about the AD converters we've talked about. We only talked about voltages. We didn't talk about an AD converter converting currents directly. No, we just looked at AD converters converting voltages, and that's okay because we have that very easy correlation. That's an absolute good way to measure currents. What else to say about those sensors? One thing is, as I already painted, we should measure the voltage in direct vicinity to the ohmic resistor. So we should not connect the voltage measurement at those places, but we should connect it directly at the ohmic resistor to get rid of the resistances of the wires connecting the ohmic resistor. Moreover, that ohmic resistor should be very exactly in its value, or at least we should know the value, the resistance of that resistor very exactly. Why? For sure, because it directly influences the accuracy of our current measurement. What else to say about that way of measuring currents? It's flexible. We can measure AC voltage, AC currents, DC currents. There's a good dynamical behavior. There's no reason which should reduce the dynamics, the possible dynamics of the system, meaning the frequencies we can measure with this system. So overall, it's a very, very good of measuring currents, with one little fact which is bad about that way of measurement, and that fact is we have to build in that resistor within the electrical network. So imagine you're in industries, you want to measure the current a machine uses. Why would you measure that current? Yeah, you know the voltage, you measure the current, you get the power that machine consumes. And so that machine already runs and you want to add that current measurement. And that gets you to the problem when you want to use an ohmic resistor, because you have to open the circuit the machine is connected to, insert that resistor, and then drive the machine again. So you change the electrical system. That's the first thing. The next thing is you're directly measuring directly at the place where the current exerts. So we have to take that voltage at that resistor in that electrical circuit. And that means thinking about the machine. The machine needs a lot of current, consumes a lot of power. We have high voltages and high currents. And now we still have to measure that voltage over here in direct vicinity of the ohmic resistor. The ohmic resistor will get warm for sure. And moreover, we have that high currents which we have to connect to. So there's no galvanic isolation and we are in direct contact to the current. That's the main problem about that way of measuring currents. For that reason, there are other ways of measuring currents, and those use indirect measurements using magnetic fields. What does that mean? Imagine there's the wire which holds the current we want to know about. And now the idea is that wire will exert a magnetic field which is radial, which is circular around the wire. And now the idea for using that magnetic field, so that's a physical fact that such a current will exert such a magnetic field. We just use I try to sketch it properly. We just use some kind of iron ring around that wire, which takes up the magnetic field. So the magnetic field will align the atomic magnets in the iron ring, which then gives us a very good access to the magnetic field in a certain distance, in a certain radial distance to the wire, which we then can measure using a Hall voltage. So we have a Hall sensor over here. And now we can just use that voltage exerted over here, for example, to get a direct measurement of the magnetic field. And by that get a direct measurement, a direct proportional value for the current. So the current is proportional to the exerted magnetic field, which is indeed proportional to the Hall voltage. Awesome. Now we can measure currents not touching the system. Coming back to that example of the machine, there's the wire connecting the machine. We just close a ring around the wire which drives a machine and can measure the current indirectly, having galvanic isolation. That's great. Those sensors bring along some problems. One problem is the dynamic range is not that good because we have some indirect measurement going on. We have some magnetization which has to be driven. What magnetization has to be driven? The magnetization of that iron ring. So for sure it will be very small in the real sensor, but still we need some time. You remember that hysteresis to magnetize that iron ring to get the real magnetic field which is connected to the current driven through the wire. I already mentioned the second problem about this, the hysteresis, which means when the current rises and then falls again, the measured values for it, for the magnetic field, will be different. We have to deal with that hysteresis. That gives us some problems, and that is the reason for the improvement of this measurement type, which is called open loop, which now can be improved in a closed loop way. Principle is still the same, only the way we deal with the magnetic field will change. Meaning, we add some coil around that iron ring we have. And that coil, the current which is driven through here, is directly connected or is directly controlled by the Hall voltage we measure. Meaning, we start the measurement by having some primary current we want to measure, which exerts a direct proportional magnetic field. Okay, that's great. That magnetic field would induce a Hall voltage over here. And now we start to exert a secondary current over here, which drives the coil, which exerts a magnetic field, a secondary magnetic field in the iron ring, which we choose to be the same size, the same value as the primary magnetic field. Meaning, we choose that the secondary magnetic field is directly proportional to the primary magnetic field, meaning we have some connection of our secondary voltage over here, secondary current over here, directly to the primary current. And now that secondary current via, for example, a resistor can be connected to a voltage we can measure indeed again. So there's some control unit in there, but this control unit means no B in the iron ring. There's no magnetic field in the iron ring because we exert a secondary magnetic field which is exactly the other way around than the primary magnetic field, by that eliminating the magnetization of the iron ring. That is for sure the better way of measuring currents indirectly using the magnetic field, using a closed loop system. Now one would say, okay, that's nice, but that looks like we get problems with the dynamic behavior. And one could say, yeah, for sure you're somehow right, but we also have dynamic problems for the open loop system. So you could for sure not say the dynamics would be better for the open loop system than for the closed loop system, because the magnetization and that hysteresis, those are bad things to deal with. Moreover, that control unit over here simply has to do nothing. Meaning, it's a proportional control unit. The Hall voltage measured over here is directly proportional to the primary magnetic field. So we just have to somehow directly connect a current source controlled by that Hall voltage. Directly proportional. There's no additional controlling or calculation involved in that system. So that control unit is quite simple, and for that reason it's quite fast. And that explains the fact that closed loop systems even have somewhat better dynamic behavior. And so those closed loop systems are the most often used system for measuring currents indirectly. Those sensors can be bought in forms of small, tiny sensors. You just adapt around your wire you want to measure the current. Or you can have some clamps. You just clamp around the wire you want to know the current. And by that, they're usable, quite flexible, simple, and are very often used for measuring as part of a power measuring unit. So power measuring unit bringing along some wires for measuring the voltage, and such a closed loop magnetic current measuring system for measuring the current. Okay, that's enough about current measurement. We are now able to measure currents directly, indirectly, in any which way, and that's an important thing, especially right now in industries, for measuring the power, and that is directly connected to the power consumption, but that connected to some other political issues, let's say it that way. Next time we'll look at some simple temperature sensors, and see you then.